So let's now, I told you just a minute ago that electricity and magnetism are connected very intimately. So what we have here is a device which is called a cathode ray tube. It's basically an evacuated tube, and we have two electrodes on both ends. And if you put high voltage across it, the electrons from one end start flying to the other end. And I can turn the power supply on by pressing this red button here, and you can see that the electrons go through. How do you see the electrons? Well, you can't actually see the electrons. What you're seeing is the electrons hitting this little whitish piece of paper that's actually paper coated with zinc sulfide or some chemical like that. And when electrons hit that, it will emit this greenish light. And what you're seeing is the electrons making a path. So the electrons are coming from here and going that way. So this is called the cathode, and so this is a negative plate. That side is positive, so the electrons accelerate towards that. So when I press this, that's what happens. So you have a beam of electrons going that way. So now let's see what happens if you put magnetic field in its proximity. You see, the magnetic field, when I showed this blue, which is the south pole, it bent down, right? Now let's see what happens if I put the other side. So this is the north pole. You see it bends up, right? The beam bends up. If I put the other side, it bends down. Even more curious is that if you put it like so, I don't know if you can see it, but nothing happens. If I bring it down, bends. Nothing happens there. And here it bends the other way. So quite complicated, right? There is a force acting on the electrons so that they are making this motion circularly upwards there. And if I change the direction of magnetic field, it's flipping. So it's dependent on the direction of the magnetic field. It depends on the fact that these things are moving. We'll know more about that in a minute. And the other thing it depends on is the direction of the motion versus the magnetic field. That matters. When I did it like this, you see the mutually perpendicular direction is where the force is non-zero. If it is in the same direction, for instance, if I put the magnetic field in this direction, there is no change. That's because the direction of the magnetic field is in the same direction as the motion of the charges. So the things that it depends on, if I may write on the board here, it seems to depend on the direction of velocity of the charges. It seems to depend also on the direction of the magnetic field. It's customary to write magnetic field as B, and both of them are vectors. It depends on both of them. It's mutually perpendicular, the force that is. So the force is mutually perpendicular to both of them. So it's actually represented by a vector cross product. It also needs to have a charge, otherwise there's no force. So that's the force due to magnetic field B. Due to magnetic field B, you have a force on charges when they're in motion, and the force direction depends upon the alignment of the magnetic field and the velocity vector, if you like. So